Freshly started SMAP Hydropower series. This webinar I'm excited to host in collaboration with IEA Hydro. Let me start by briefly explaining this session structure. So first you will hear from me and Klaus for a few opening remarks. Then our presenters will present different cases. And then finally, we will have a Q&A session, and we encourage our audience to write their questions in the chat. Please feel free to write your questions during all the presentations, and then we will try to address as many of them as possible at the end. I would also like to remind everyone to please keep your mics muted so that we avoid background noise and interruptions. And then I would also kindly ask all of our presenters to keep their video on during this session. But now we're ready. So I would first try to give a slight background from our perspective with the topic of today's webinar. This one seeks to explore the evolving role of hydropower in the energy session. So as the transition towards sustainable energy accelerates, hydropower is also recognized as a key energy source that will enhance power system flexibility, reliability, and also resilience. This becomes increasingly important as the growing share of variable renewable energy sources like wind and solar increases the need for dispatchable power to balance power system. So during our first webinar, you will learn more about this evolving role and how it's transitioning from a conventional energy generation role to a critical provider of flexibility and balancing services for modern power system. And you will also explore and hear more about the best strategies for hydropower development, explore some case studies, practical solutions, and so on. And by that, I would like to welcome Klaus from IEA Hydro to give his welcoming remarks. And Klaus is also a civil engineer who has more than 37 years of experience with all aspects of hydropower development. He is now the Executive Committee Secretary for IEA Hydro, and he also operates his own small hydropower plant in southern Germany. Over to you, Klaus.
I'm going to share my screen. Thank you. Here we go. Thank you, Bente, for the introduction. So I will, as my opening remarks, I will present you a little bit about the IEA Hydropower Technology Collaboration Program.
You're muted, Klaus.
Okay. Can you hear me now?
Yes.
Okay. Did you hear my opening words? Okay. Okay, I would like to tell you a little bit about the IEA Technology Collaboration Program on hydropower. If we look at the global context, and Bente already mentioned that, IEA has published a report in 2021 which says if we want to reach net zero greenhouse gas emissions from the energy sector by 2050, we need to double globally installed hydropower by 2050 as compared to 2021. So we have to build in less than 30 years what we built over the last 100 years. So that's very challenging. Mostly in Europe and North America, where we have aging hydropower fleets, this will be refurbishing, upgrading, and some new ones. But most of the new development will be in Asia, Sub-Saharan Africa, and South America. We are presently lagging behind by a factor of 2 to 3, so we are way too slow in implementing the hydropower that we need. Generally, as Bente already mentioned, we need more storage, more flexibility, and we have to implement highest sustainability standards. And that's because of the integration of the new unregulated renewables, solar and wind, which will be the main providers of renewable energy. So hydropower plays a key role in this transition, and it changes from being a provider to being an enabler of this integration. So that's very relevant. Now it's okay. It's a little bit delayed here. I'm sorry. If we look at the members of IEA Hydro, we have 9 active members. You see the countries on the map and on the list, and we have one sponsor. That's a private utility, that's Sarawak Energy from Malaysia. The countries that we have listed here, it's a small number, but they are representing well above 50% of the globally installed hydropower potential. So it's quite significant what we have here. And of course, we are looking for new participants. The technical work is organized into tasks. Tasks are basically working groups. We have presently 5 active tasks. They are shown on the slide here. Task 9 is one of the oldest ones, looking at valuing hydropower and flexibility services, and we'll hear about that more in the next talks. Then we have 16 on hidden and untapped hydro opportunities. 17 looks at climate change. 18 is looking at how to make decisions in very large catchments, very large basins with multiple dams and hydropower plants and operators. And task 19 is looking at hydropower and fish issues. And it's very weird because it's not moving ahead, and I don't know why it's not changing the slide. Now it does. Okay. The strategic work plan, which we have for the next 5 years, has 4 main topics. The first one is flexibility and storage, and you see a whole list of sub-themes which are included in this overarching theme. Then we have a number of issues on climate change impacts, including reservoir sedimentation, but also strengthening the resilience against climate change. We have some sustainability issues, which have some overlap with climate change resilience, of course, but hydropower and fish is a remaining big issue. And then we have this topic on hidden hydro, which mostly looks at hydropower at existing infrastructures, but also expanding existing hydropower plants in the way they operate, and they provide storage and flexibility, even if they are not really designed for that. We also added a small pumped storage component to that theme. And then we have some overarching components like digitization, artificial intelligence, better alignment with the IEA mission, communication, dissemination, increase the visibility, looking for new participants. So that's kind of overarching apart from the technical issues that we are looking at. This is all distributed across the different tasks. So several tasks include some tasks include only one of the overarching themes, and other tasks, they are quite wide. They have all kinds of components included. So that's you can see that on this slide a little bit how this is to be understood. We also have general non-technical activities. That's basically looking at outreach, organizing collaboration with other multinational hydropower organizations, a better communication strategy to get our work and our results out into the public, and to increase political awareness on the importance of hydropower. So that's something we do with others together. And that's already the end of my short introduction, and thanks very much.
Thank you so much, Klaus. And I really appreciate that we are able to listen to and draw on the experience from IEA Hydro. And I think that we will now turn our attention to our first presenter, who is Lynn Amelia Schaefer. She's a researcher at Sintef Energy Research, and she's been there since August 2016. She's also holds a PhD from the Norwegian University of Science and Technology on the topic of modeling of environmental constraints in hydropower scheduling. So she contributes to the work in IEA Hydro with focus on the role of hydropower as a producer of renewable energy and flexibility services. And by that, I will hand it over to Lynn Amelia to start her presentation.
Thank you, Bente, and thank you for that introduction. I'll just share my slides here. Okay. Yes, so as Bente said, I will say a bit about some of the work that we have done in IEA Hydro Task 9 on defining the need for flexibility in power systems and in changing power systems. And as let me see, there we go. Yeah. So first of all, I think we had a very nice introduction to the technology collaboration program by Klaus here. But task 9 is about valuing hydropower services, and we have focused on two main topics: flexibility for integration of renewable energy and flood control and drought management. And then today we're focusing on the first of these. And during the last few years, we've published several reports and white papers related to the topic of this need for flexibility, and also how hydropower can contribute into this. So I will come a bit back to some of this in my presentation now. The background of this is, of course, the deep decarbonization of the energy system. And I think you've all seen this kind of plot before. There are a lot of different studies of how this will evolve into the future and towards 2050, but the main takeaway is that the need for electricity is increasing, and this needs to come from renewable energy sources, and we know that and a lot of it has to be covered by wind and solar power, which are variable renewable resources. And we're also decommissioning or taking out a lot of resources today that are flexible. So the need for flexibility is increasing, and also we need to supply this in a different way that we have done traditionally. Okay, now it's okay. Yeah. So flexibility is a very broad term. I have some figures here from the European Commission from their recommendations on energy storage. So they estimate that the European energy system will have a share of renewable energy of 80% by 2050, and that this will lead to a need for flexibility of 30% of demand. And also, since the electricity system is since the need for flexibility is increasing, this means that the amount of flexible energy services also is increasing quite a lot. So a broad definition of flexibility of a power system can be, for example, this: the extent to which a power system can modify electricity production or consumption in response to variability, expected or otherwise. So this is a definition from IEA, but it's still very broad, and it's still holds a lot of different type of challenges to the power system. So in our work in IEA and the workshops and discussion that we have tried to describe this closer and define it into different type of products and challenges. And one of the frameworks we've used has been these definitions from IEA on different phases of integration of variable renewable resources, where you can divide this transition into these 6 phases, where in the early phases there are not that many challenges to the power systems. You can operate more or less the same or with just smaller adjustments in your operations. But then when you come into phase 3 here, we see that variable renewables are more and more determining how you operate your system and how all the other resources in the system is operated. And then in phase 4, you start to see additional needs for investments in flexibility to balance the system. And then in phase 5 and 6, there are more structural challenges on both surplus and deficits that can last in longer periods, weeks, and also there can be seasonal challenges. And then to the right, we have a mapping of different countries or system in different countries and which phase they're in. But this was done a few years ago. So I think we already see that some of this has changed, that some of these countries have moved and are now in new phases where they're seeing other challenges. For example, several countries are having these surplus periods, and some are also experience longer periods with undersupply from renewables causing challenges. So this one way of structuring flexibility is on time scale. So you could divide it into the need for short-term flexibility and medium to long-term flexibility. And we have defined short-term from being from sub-seconds to minutes to hourly scale. And in this range, you have challenges related to system stability, frequency control, and rapid fluctuations in supply and demand that needs to be balanced. And then as you progress towards medium and long-term flexibility, you have different challenges that are more energy related. And you have these longer periods of surplus and deficit that causes problem for the system. And just to say that we are not the only one operating with these kind of definitions. This plot is from a study from JRC on flexibility requirements and the role of storage in the future European power system. And here you also see that this need for flexibility, it's expected to be both on a daily, weekly, and monthly level. So we need to be able to shift energy on many different time scales.
I think that we need to progress now, Linnea.
Yes, but it is 12 minutes, right?
Yes, but please keep that in mind.
Yeah. Okay, and then we have you can also look at the capability of the flexibility resource. So you have different types of requirements to the services that are delivered. So it can be the preparation period, how quickly you can ramp up or down, the maximum power that is delivered, the total energy that is required to deliver the service over a certain amount of time, and then also the deactivation period and if there is a need for a rest period or how often or frequent this service can be supplied. Okay, so I thought I would go into 2 very well-known challenges due to variability of wind and solar power. So one is the duck curve, or how the daily operational profile is changing due to solar power. And due to when the sun, as you get more solar into your system, you get this very rapid power, or this power production is increasing rapidly in the morning when the sun rises, and you need to ramp down other resources quickly. And similarly, you need to ramp up other resources quickly when the sun sets in the evening. This can be challenging. And also in the middle of the day, you can have surplus challenges or very low net demand, which is causing issues because you might have other resources like baseload generation that requires to operate more stably through the day. The advantage of this is that solar power is perhaps more predictable than wind power. So it's possible to prepare for these kind of changes. It's just a different way of operate than what we've done more traditionally. Another challenge that is receiving a lot of attention now is Dunkelflaute events, and we're seeing them happening more in different systems where you have longer periods of low wind production, which is causing an energy deficit. And this can last for several days and even weeks. So to the right here, you see some simulations based on how the weather year of 2001, but for a system with more wind than we had in 2001 in the North Sea. And you can see these long periods happening. And in task 9, we've looked more into this. So Abhishek Sumani is coordinated a work on this of resource drought and the need for long duration energy storage. And I think this will be very important now. It's already becoming important, and it will become even more important as we have larger shares of wind power coming into the system combined with solar power. And the plots here are from this study, and they are for the Californian system. And they have looked at historical data and counted how often these resource droughts were occurring in the historical data. And we can see that there are quite many events ranging from 4 to 16 hours. And there are also a few events lasting longer than 16 hours in this system. And you can also to the right see the total energy deficit. And in this, or in the current system in California, this contributed to a drop from covering about 8% of load to 1% of load. But you can imagine if wind power is covering a much larger share of the load, it will be very challenging to meet these large amounts of energy over a longer period when you have these drought periods. So this is something we also want to focus more on in IEA Task 9, IEA Hydro Task 9 moving forward.
Thank you so much, Line Amelia, for a very good presentation. And by that, I would also like to welcome Dr. Elena Vagnoni, who is currently the head of research project at EPFL Technology Platform for Hydraulic Machines. She's also a lecturer for the EPFL Mechanical Engineering section, and she has had different positions, and one of which is a research assistant fellow at Johns Hopkins University, as well as a fellow guest scientist at NTNU. She's also currently the vice coordinator of the European Energy Research Association Joint Program on Hydropower. So by that, I hand it over to Elena.
Thank you very much, Bente, for a kind introduction, and good afternoon from European time to all of you. So my presentation will talk about how hydropower can actually contribute to flexibility. So thanks, Lina Amelia, for the excellent introduction. So I will not spend too much time in saying that the decarbonization is happening, and we definitely need the endorsement of flexibility and reliability to guarantee the security of the power system. We understood that flexibility is needed because of a set of different short-term and long-term basket of products, which goes from Substack on 2 years. We call about ancillary services, all those services so that different kind of energy sources can provide to the grid in order to balance both voltage and frequency across different time scales, so from sub-seconds to hours. And then we also have another kind of flexibility services that are needed to guarantee the adequacy of energy supply to the grid, and that goes so from day to years. Hydropower is actually key in providing all these different grid services, and hydropower is also the only renewable energy source that allow for providing all those different services to the grid. So it's really a key energy source that we should endorse in order to allow energy transition happening. Unfortunately, this provision of ancillary services and more generally of flexibility doesn't come for free for hydropower. Especially we look at what happens to hydroelectric units. Those are today strongly stressed because they do not operate anymore according to their design condition. Typically, we had hydropower operating into a single optimal point with a tiny region area around that, entailing so for good flow conditions, for instance, in hydraulic machines. Because of a new need of the grid, because of this need of flexibility and dynamic changing in operation, more frequent startup and stop cycles, etc., we are asking hydropower to operate into multiple points that actually do not coincide anymore with design conditions. Also, on the top of this flexibility burden, we also have new challenges in hydropower technology coming from both sustainability requirements and resilience to climate change. So all those new operational requirements, exactly what do they represent for hydropower? They represent extended operating range, more frequent transient operations, for instance, startup and stop cycles, changing mode from turbine to pump, etc. in case of pump storage, efficient water management. And there is so a strong need to provide new technologies, advance so the science behind to comply with the new industrial needs. So that entails an optimization, for instance, of power plant operations, so new methods to steer operation, new monitoring tool, as well as new maintenance strategies that takes in consideration not only efficiency, but also, for instance, wear and tear and vibrations, water management, etc. And also novel technologies, design and materials that are so more compatible with those new paradigm shift in operation. With this introduction, so I'm very happy to introduce to you the recently completed X-Flex Hydro project. So that has been an European project funded for 4.5 years, putting together 19 partners from academics to key industrial players to demonstrate how hydropower can actually extend power system flexibility. All solutions that were out of the first phase of the project on innovation have been demonstrated into 7 demonstrations, so 7 hydropower plants from run-of-river storage and pump storage hydropower plants. And the last phase, where all different technologies demonstrated on site have been also deployed for a future adoption in the markets. So what I'm going to present in the next few slides is what did we implement? So what are those innovative technologies that allows for extending hydropower flexibility? What are the main results of demonstrations with a few examples, and also how we can exploit them beyond? So the first technology that was defined, improved, and demonstrated was the hydraulic shear circuit, applied for pump storage power stations featuring more than 1 unit or featuring 1 ternary group, for instance. This was demonstrated in Grand Maison, France, but also in Frades and Alqueva in Portugal. Each of the power plant has different features. The main benefits for this technology is that allows for extending the operating range and allows for regulation in pumping mode, provide frequency control in pump mode, and also allows for a faster switch from pump to turbine and vice versa. So just to make it sure that you understand it correctly, what does it mean hydraulic shear circuit? It means the simultaneous pumping and generation from two different units. So if you have, for instance, two reversible pump turbines, and you have it in this example, it means that one operates in pumping mode, and then part of the flow, instead going back to the penstock, recirculates in the second unit, which is generating. Since the generation can be variable, you can control generation, you automatically put an offset on the pumping of the overall power station. Thanks to this, so you improve synchronous inertia and you enable all different ancillary services, so from primary to tertiary frequency control, also in pumping mode that otherwise won't be possible. As an example, as I said, this was demonstrated in several plants. In Grand Maison, this is in commercial operations since September 2021. And it was demonstrating so that the balancing power was extending up to plus minus 57 megawatt, and also that the hydropower circuit during commercial operation accounted for 55% of the time in pumping mode. So definitely worth investment for a commercial operation. Another flexible technologies that was demonstrated into this project is the variable speed. So there are many plants already equipped with variable speed, mainly for efficiency purpose and extension of operating range. But we demonstrated that there are many other benefits that variable speed technology can provide to, in this case, pump storage power plants equipped with reversible pump turbines. So at the top of extending the operating range, enables also regulations in pumping mode, allows for faster regulation in respect to fixed speed machines, improved operation at partial load, so giving more guarantees on the safety of the machine if we decrease the power production in respect to nominal conditions, and allows also for minimized fatigue trajectories. So fatigue in terms of wear and tear, so on the hydraulic runner. Overall, this also means that we can improve, thanks to variable speed, primary frequency regulations, black start capabilities, and voltage control. And we can enable all frequency regulation control in pumping mode, again, thanks to the ability of changing the speed through full-size frequency converter or an asynchronous motor. As an example, this was demonstrated in Zmut power plant. The key outcome of this is that we demonstrate that this 5 megawatt variable speed turbine can be put successfully into commercial operations, and that the startup sequences has, you can see here in this graph, few trajectories to start up the machines that were studied and tested. We demonstrated that thanks to variable speed in respect to a fixed speed machine, we can decrease up to 15 times the damage during such a startup operation. And also we can decrease up to 3 times the startup duration. So we can be faster in answering to the request of the grid. The last technology that we demonstrated was a hybridization with battery. In this case, so we have a battery energy storage system coupled to one Kaplan unit, demonstrated in one run-of-river power plant in France, Fogelgrün. Benefits are the reduced wear and tear on hydraulic components, a faster provision of frequency control service, because those are all the Kaplan unit with a particular big diameter. So they are not very reactive in respect to the control commands, and also the enhanced regulation margin. In terms of grid services, what those benefits allows for is to improve primary, secondary frequency control, and also black start capabilities. They enable, so this plant was not able to do that before, synthetic inertia, and also primary control. Here you can see a few results from this demonstration of hybridization in Fogelgrün. So first of all, fast dynamic frequency response was allowed. So now this power plant has new capabilities in respect to the transmission system operator agreement. And these new flexibility requirements and capacities also come with a reduced need of maintenance from the turbine side, because the use of a battery, while increasing the participation to primary regulation, also allowed to reduce the wear and tear, where the wear and tear on the Kaplan units is counted in terms of number of movements of guide vanes and blades. So here you can see the comparison between two different control algorithms that were developed to steer and dispatch the power between the battery and the hydro unit. And with a fuzzy logic, we were able to reduce up to 82%, 77% with hybridization or on blades and 82% on guide vanes, while with double layer model predictive control, we were able to further reduce this on both guide vanes and blades up to 96% of the mileage.
Just wanted to give you a kind reminder. There's 1 minute left, Elena.
I just a couple of slides left. Thanks. And just to have an idea, the investment cost, so the capex cost on the battery, are estimated to be paid back in 4 years of operation, thanks to the revenue in FCR markets, but also reduce maintenance costs and reduce the risk from turbine failure. Digitalization, of course, is also key. So the Smart Power Plant Supervisor, that is our digital tool that allows to integrate turbine dynamics and condition knowledge into the advanced control unit and operation, as well as in maintenance, predictive maintenance. It's also a tool that allows for improving flexibility of the machine, so improving the quality of all ancillary services provision while reducing the cost, the OPEX cost on the machine. So I won't have time to go through all the different results of our project. Here, for instance, you have the permission of extension of operating range without any further technology. So just by integrating condition knowledge of the machine, by decreasing, for instance, the number of startup and stop cycles and better dispatch, applying the same.
Thank you so much, Elena, but I'm afraid that we need to continue on to the next one. Even though I would have much appreciated to hear a lot more about all of these very interesting results from your research in XFlex.
This does brings to the conclusion slides. And thank you very much for your attention.
Thank you, Elena. And by that, I would also like to then welcome our last presenter, Katarina Kimmele. She's a globally experienced energy policy expert with over 15 years in the sector. She's currently the acting executive general manager of strategy at Hydro Tasmania, where she leads the teams across major projects, strategic delivery, planning policy, and organizational change. She's a strong advocate for sustainable hydropower. And she's also very passionate about showcasing hydropower's unique abilities to contribute to the energy transition. So with that, I hand the floor over to you, Katarina.
Thank you. I hope you can see my presentation. I'll just go in the slide mode. If I can click on this button, doesn't want to show, but let's try this way. All right, perfect. So welcome, everyone. Thank you for having me. I'm Kat Kimmel, and we hope that this presentation will give you an understanding of how Hydro Tasmania is navigating the energy transition. We have been powering Tasmania for over a century, starting with our first hydropower station in 1916. Since then, we have evolved alongside the changing energy landscape, always focused on delivering clean and reliable power. Today, as we navigate the transition, we are modernizing key assets like Charlie and Safana, ensuring our hydropower system remains strong, efficient, and ready for the demands of tomorrow. So first things first, who are we? So Hydro Tasmania is Australia's largest generator of clean, renewable energy. We are government-owned business. What that means is that we operate as a commercial entity, but our profits go back to the people of Tasmania. We are owned by the state, with our shareholder ministers effectively our shareholders. We make decisions that balance commercial priorities with the broader interest of Tasmanians. We manage over 50 major dams and 30 hydropower stations, generating around 9,000 gigawatt hours of renewable electricity each year, providing not just clean energy, but also flexibility and storage needed to keep Tasmania and the national grid running smoothly. We are also evolving. Two major developments, which I'll touch on shortly, will reinforce our role in securing reliable energy future. Our impact also goes beyond Tasmania through the existing interconnection Bass Link to the mainland Australia and the future Marinus Link that's currently under development. We are expanding our ability to share the energy with the rest of the Australian national electricity market. So you might say we are small, but I would also say we are mighty. So first things first, let's start with the first case study that's very close to our heart. This is a Taralia hydropower scheme, which has been providing clean and reliable energy for over 85 years. The scheme is a true piece of Tasmanian history, made up of 3 power stations with a combined peak capacity of 100 megawatts. One of the standout features is the beautiful Art Deco building, which you can see on the screen, is a symbol of craftsmanship that has powered Tasmania for generations. These stations are fed by a large natural headwater storage at Lake King William that flows through the system of conveyances, canals, and pipes to the stations downstream. But what's really exciting is the redevelopment we are currently undertaking, which will nearly double the peak capacity of the scheme from 100 megawatts to 190. And also this modernization will not only increase this capacity, but also make the station more efficient. By introducing a pressurized conveyances system, we will be able to generate 30% more electricity from the same amount of water. This will make the station more flexible, allowing it to better respond to market needs and help manage the increasing share of VRE across Tasmania and Australia mainland. Sustainability is also what we do. It's at the core of what we do, Preserving Tasmanian unique natural heritage is a responsibility we take very seriously. This Taralia scheme is located very closely to the Tasmanian Wilderness World Heritage Area. The ability to control more precisely the flow of water through the scheme will minimize the risk of any potential environmental impacts on the area. This project is currently going through approval processes with expected completion date in 2030. So the next case study that I would like to talk about is another part of our operations. It's the system of shallow storage run-of-river dams and power stations along the Lower Derwent River here in Tasmania. Unlike Taralia, and you can see it on the screen here, that's the station that I was just talking about. So that's the, I hope you can still hear me.
Yes.
Oh, sorry, I might have lost you for a second there. So the Lake King William here, that's the storage that I was talking about. And then the Taralia power station is located down below here. So the Lower Derwent system is just located just below it. And it's all of these little small tiny storages that are powered. They are smaller, but just as important. You probably know that hydropower is more than just about generating electricity. It plays critical role in providing essential power services. That's exactly what this Lower Derwent scheme does. They provide something vital to the grid, which is inertia. And this is further supported by a wide range of synchronous condenser functionality across other assets, ensuring that Tasmanian energy system stays stable. And Lower Derwent is just one example. Although not illustrated on this slide, many of our northern Tasmanian assets and our highest capacity dam, Lake Gordon, are essential to critical service like Black Star capability. This means that if the system experiences a regional or systemic shutdown, Hydro Tasmania is the sole contractor provider in the States to help to bring it back online. This kind of reliability and flexibility, what makes hydropower a cornerstone of Tasmanian and national power grids. So the next project, finally, that I would like to talk to you about is the energy storage, something that becomes more and more crucial and important as the power system evolves. We heard from other presenters that storage and the increased penetration of VRE is just something that our system needs to cope with. And Tasmania is strategically positioning itself to be a multi-purpose provider, balancing baseload energy, flexibility on ancillary services, and critical energy storage. So at the heart of this evolution is our Lake Savannah Pump Hydro redevelopment redevelopment project, This project is an exciting step forward. It will make use of the existing Lake Savannah as a lower storage, while a new upper storage will be built on the western side of the lake, creating a powerful, flexible energy storage system right at in the heart of Tasmania. This project is currently progressing through local and federal regulatory approvals, but once completed, Savannah Pump Hydro project will operate as a long-duration energy storage with capacity of 750 megawatts and a duration of 20 hours. This deep storage will be vital in supporting the integration of VRE both within Tasmania and in Australia. It will be also important in allowing Tasmania and Australia to weather low winds and low solar events that are projected to only accelerate over the coming decades. So where does that leave us? I suppose it brings us back to the starting point. How does Hydro Tasmania plan to navigate this energy transition while balancing the rich legacy with the modernization? We are excited about the journey ahead. We are in a unique position to leverage both the existing and future assets, along with the skills and passion of our people, to provide energy and flexible services and storage solutions that Tasmania, Australia, and even the world will need to operate a sustainable, efficient, and reliable power. We hope that what we are doing here in Tasmania on this small island can serve as a model for the world, showing how we can meet the urgent need of global energy transition with innovation, resilience, and a commitment to the future. Thank you, everyone. I felt like I've done fit my 8 minutes there.
Thank you so much, Kat. I truly appreciate it. And by that, I think that we will start with the Q&A session for today. So I would really encourage all of our participants to start typing in questions in the meeting chat. And I believe that I also get the pleasure of asking the first question. So, Kat, I was wondering, are there any particular or more important policy changes in Australia that has led to any strategic change in how you develop your hydropower projects?
I think there's still some challenges in terms of the hydropower. I think there's still some lacking support for the long duration storage. And I think that that's something that we heavily advocate at the national level and just the global level in general. There's been some policies like LTSS, a long duration underwriting support mechanism that's been introduced in Australia in some regions, which help to support some of this long lead, construction costs and projects in general. However, they're still quite partial and not consistent in nature. So that's something that we are definitely, it's on our mind, and that's something that we are quite vocal about as well. You're on mute, Bente.
Thank you. I think I would like to follow up on that and also ask Klaus, because you are now based in a different part of the world in Europe. So I was wondering if you also observe if there is any differences in policy between Europe and Australia that would enable implementation of flexible hydropower.
Well, I cannot speak for all 29 or whatever European countries, but some countries, most countries have acknowledged that technically it's necessary, but the problem is that the business case is not there in many of the countries, and that utilities, they have to make a decision based on taking on some of the taking on the risk or a large part of the risk themselves. because they see the necessity that the storage and the flexibility needs to be there, but the business case with the existing markets is not clearly visible. So I think this is one of the problems which we have in some of the countries here. Nevertheless, we have investments in pumped storage hydropower plants quite a bit, for example, in Switzerland and in Austria. But there are also other opportunities that are not being used. Although the potential is there, but the business case is not clear enough, and the signals from policy makers, it's not very clear.
Well, I find that that is a very interesting input. And Kat, maybe you could share some insights on, more particular towards pumped storage hydropower in Australia.
Sorry, I got disconnected there for a second.
No worries.
Could you,
yes.
Yeah, go ahead. Could you just repeat the question?
Yeah, so at the end of what Klaus said, he highlighted that the policy for decision making and the business case for pumped storage hydropower could probably benefit from becoming more clear. And I was wondering if you would like to contribute to that perspective, given the context in Australia, where there is now a larger investments in pump storage hydropower, and if there's anything that we can draw from that.
Yeah, I guess in reality that a lot of the pumped hydro storages right now that's been developed in Australia actually been underwritten by the government itself. So I think that that's something that to keep in mind. And I think the reason for that, as I pointed out before, is that because there is quite a significant lead construction sort of time, you need up to 6 to 7 years at least to build one. So as a private investment, you need that certainty. So which makes it a bit tricky for other developers to go in and invest. So some of these policies that's been introduced that we've seen being successful are the ones that provide that revenue, I guess, cost protection, I would say, the downside risk really with the sort of support of at least 15 to 25 years. And I think that that's something that's been quite important for a lot of investors in Australia in particular. So we only seen one project right now that actually was successful, that went through the LTESA in New South Wales. That's a private investor, so the private company is building that, not government. And again, they still have to take quite a significant risk through that process as well to really, I guess, take this project forward.
Thank you so much, Kat. I think that to bring it down from, high-level policy discussions, we do have also received more technical questions from our audience. So I think I would really like to pick up on one of these questions that comes from Ramiro, and I would like to address that to Elena. So this applies more to what is the usual efficiency of pumped storage hydropower, and what is the optimal head for pumped hydro. So I think that the case here is coming then from Andes, where there is a height difference of 3,200 meters.
Mm-hmm. Well, so of course, it depends where I'm not familiar with the Andes scenarios, but for efficiency of pump hydro storage, it depends if you refer to generator pumping or to overall cycle. Normally for generation, so we consider, for instance, reversible pump turbine or ternary groups. We are in global efficiency that are on the order of 80%. Of efficiency, again, not considering, of course, the pumping part. For pumping, we are a little bit lower than that, as normally pumps are less efficient than the generating units. But it depends a lot. It depends on the hydraulics layout that you have, so on the head losses, on the machine performance, the age of the machines. So there cannot be an overall answer to this question. And what's the optimal head for pump hydro? Well, the world record, I think it's held in Switzerland. It should be close to 2,000 meter head. And for this, you definitely need Pelton units from generation. And for this kind of high head, so for all machines that are above of 800 meters, definitely you will need for Pelton units. So ternary pump hydro would be the optimal setup for this kind of head. I would answer the other way around. So not what's the optimal head, but what's the technical solutions that allow to have optimality depending on the head. If you have a lower head, then we would definitely go for more kind of Francis types machines, so more on reversible units or quaternary groups.
Thank you so much, Elena. I think that there is also very other specific technical questions, and I do really appreciate that we can get down to this level also in our webinars. And this applies also to how the cavitation phenomenon change if you compare storage hydro to normal regular runners.
Mm-hmm. So if you have, let's say, well, I don't know what exactly you mean from storage hydropower runner with normal run. What's normal runner to be?
I think that if you compare a pump storage runner with a Francis runner.
Okay. Well, both suffer of cavitations. If we consider, so for instance, reversible pump turbines and classical Francis turbines, but definitely both can suffer for cavitation. The most risky part in pump storage is the pumping mode, because the cavitation at the inlet of the pump then cause strong erosion, cavitation erosion on the runner. So it's definitely the part that you want to really avoid for maintenance purpose. While in terms of general cavitation, both standard hydro, so for example, take Francis or pump storage, then that would lead to vibration and pressure fluctuations that are both harmful in the same way, but in different range of operations.
Thank you so much, Elena. I think that we're going to wrap this up with one more question, and I think that we start there with Linda Melia. So in your presentation, you highlighted the fact that it is important to evaluate flexibility across timescales. And then one of our questions now from our participants is also related to climate change. And I was wondering, from your perspective, how would you consider climate change in terms of the timescales, and where you would do more modeling to explore this more in detail on how hydropower can contribute to mitigate?
Thank you for that question, and that's very interesting. I think with climate change, this will also depend on where in the world you are, because climate change will have so different effects depending on the climate you're in. But it is definitely changing the seasonal patterns we're seeing, so kind of the long-term or the yearly and seasonal trends, but it is also changing the short-term patterns that we're seeing. So for example, in Norway, where I'm located, we see these more intense short rain periods, but we're also wondering how will this change the snow melting period in the spring, the snow storage that we have through the winter. And these are questions that we need more research on in general, I think, both for the short term and the long term.
Wonderful. Thank you so much. So in short, then, that what you try to allude to is that then it really affects both on the seconds and the short term of the time scale, even through seasons, and then also annually. And by that, I think that we will try to wrap up today's session. First, I would like to extend a very warm and heartfelt thank you to our esteemed presenters. I think that we have learned today that there is a larger need for utilizing the flexible hydropower, and that also it can bring many benefits for enabling the energy transition. And then I also would like to inform everybody that, as I said in the beginning, we are starting up a webinar series. So stay tuned for the next webinar that we plan to host in the coming months. So I look forward to seeing you there as well. And by that, have a good day and evening and night, everyone.
Thank you, guys. Thanks.
Thank you. Bye.
Thank you. Bye.